All right, guys, we are back with another video. That is, we're going to discuss about the beats. Actually, we're going to talk about the beats that occurs between two different frequencies, right? So how a beat could occur, and then like the questions related with it, right? So I guess most of you guys might be somewhat okay with the theory behind beats, because like it's not very complicated, right? So like in order if there is like two uh, if there is like two tuning forks, right? So which has a frequency f1 and f2, the beat frequency between them is going to be like f1 minus f2, right, in the modulus, right? So this is pretty basic, right? So I guess the theory is somewhat quite familiar with you guys, but let's go for some questions, right? So let's go for some questions and see how it is. Right. So let's go for the 15th question, right? In the theory class, of course, I guess I discussed the 14th one. So let's go from the 15th question onwards. I think these are pretty easy beat frequency questions, actually. Anyways, it says metal wire of diameter 1 millimeter is held on two is held on two knife edges separated by a distance 50 centimeters, right? The tension in the wire is 100 newtons, right? So, okay, the tension of the metal wire is 100 newtons. The wire vibrating with its fundamental frequency and a vibrating tuning fork. Okay, along with this vibrating wire, another vibrating tuning fork is placed, and that tuning fork, like, so the wire is going to vibrate with a certain frequency, and the tuning fork is going to vibrate with a certain frequency. So when these two frequencies are somewhat closer to each other, you're going to hear, like they have said, it produces 5 beats, which means the beat frequency is 5 hertz, right? So then they are saying next, then the tension of the wire is reduced. Okay, the tension of the wire is reduced. All right, let's see what happens when the tension of the wire is reduced. And then at that state also, the beats that heard was the same. The beats, like even after decreasing the tension of the wire, still the beats that heard was the same. How come it's possible? As the first question, they're asking to find the frequency of the fork, right? So let's go for that problem, right? So it's like this. It was the 15th question, right? Yeah, 15th one. So it's like this. Now there is a certain wire, right? There is a certain wire, and with that wire, a tuning fork is vibrated. Initially, the tension of the wire was what? 100 Newton, right? The tension was 100 Newton, and then the length was constant, and the diameter was constant, right? So all these things were fine. The length and the diameter, they do not change. So let's assume the frequency. Let's assume the frequency of the tuning fork is f, right? Let us assume the tuning fork of the frequency is simple f, right? Then what? Like initially, when these two are vibrated together, when both these are vibrated together, the wire as well as the tuning fork, and then also they have told that this is vibrating at its what? Fundamental resonance state, right? Fundamental resonance state. So when this is vibrating and this is vibrating, you hear a frequency. What? You hear a frequency of a beat frequency of 5, right? So let's assume this is f1, and let's assume this is f2. The frequency produced by the wire is f2. So let's consider f1 minus f2, right? f1 minus f2 is equal to 5 hertz, right? So like obviously f1 minus f2 is what? The beat frequency, fb, right? So f1 minus f2, the beat frequency is what? Exactly, it is 5 hertz. 5 hertz. All right. Okay. So fine. Next, what happens? Next, they are saying, now this is one equation, right? One equation. Next, they are saying the same wire, right? Same wire, but when the tension is reduced to T2 to 81 hertz, when the tension was reduced to 81 hertz, tension was reduced to 81 hertz. Sorry, not 81 hertz, 81 newtons, right? When it is reduced to 81 newtons, all right. So now also, when you vibrate both together, both hear the same frequency. Now the frequency of the tuning fork didn't change. It is always F1. It was previously also F1. It is F2. When the tension of this guy changes, when the tension of the wire changes, obviously the frequency of the wire will change. That's pretty sure, right? So like we know the fundamental frequency is written now. The fundamental frequency of a wire is written 1 over 2L root T over M, right? So here L is constant, M is constant, root mass per unit length is constant. So therefore, like we can say frequency is directly proportional to the tension, right? So actually from 100 to 81, the tension has decreased. So therefore the frequency should decrease from F2 to, it should decrease, right? It should decrease actually. If this was F2, now it should be some other value. But even though this changed, let's assume now the new frequency is F3. Even though this changed to F3, the beat frequency between them remains the same, it seems. How is that possible? Like if at least one of these guys change, if F1 is the same, if F2 changes, how come it still gave how come it has given how come it still gives 5 hertz to beat frequency, right? It may be like this, it may be in this way, right? So this is the only possible way, right? So actually this equation is not correct. Actually it should be in this way. Like initially the F2 frequency is higher than F1. This should be the case, right? F2 frequency is higher than F1 frequency, which means F2 minus F1 should be 5 hertz, right? This is the first equation. This is incorrect, right? This is incorrect. Why? You will see why, right? So initially F2, this wire's frequency is higher. This F1 is lower. So the difference gave 5 hertz. We can assume it as that. And then next what happens is when we decrease the tension from 100 to 81, right? When we decrease the tension, frequency should also decrease. So F3, the frequency of the wire decreases from F2 to F3, right? So now what has happened is this F3 is less than F1. F3, this frequency is less than F1, right? So now what has happened is F1 minus F3 gave 5 hertz. This should make sense actually, right? You guys are 11 students, like it should make sense now. It's like this. Initially, let's assume the tuning fork had a frequency of 250 hertz. This is for example, right? So when the tension was 100 hertz, 100 Newton, the string had 255. When the tension decreased to 81 Newton, now the now the current frequency is 245. It's fine, right? 5 hertz, 5 hertz. Right? So this example makes sense, right? So I guess it's fine, right? So yeah, I'll move on to the question once again, right? I hope you understood, right? So now we have two equations. This equation, right? So two equations, but too many unknowns, right? 1, 2, 3 unknowns are there. So we will make use of the tension actually. We'll make use of the tension. In the first place, right? So we know that frequency is directly proportional to the, like, since it is vibrating with its fundamental resonance state, right? We know that the frequency of the tuning wire is directly proportional to the root T according to this equation, right? The fundamental frequency equation, right? So in that case, we can say for the first state is what? F1, right? F1 is directly proportional to the 100, and F3 is directly proportional to the 81. So F1 over F3 is root 100 over 81. This is what is this? So this is F1 over F3 is equal to 100, root 100 is 10, 81 is 9, right? So what we can do is F1 is equal to F3 times 10 over 9. Now we have the third equation. We have three equations, right? We have three equations, three unknowns, three equations, three unknowns, right? What we need to find is the, what do we have to find? We have to find the frequency of the fork, frequency of the fork, right? So let's find that. Frequency of the fork is F1. We know sorry, it's not F1 here. This is F2, right? This is F2. This is F2. So this is F2, F2, right? So the thing is, we will find F1 now. F1, let's find F1. F1, how to find F1? Like in this equation, let's substitute as, okay, now you know, right? Like I will not teach you how to substitute and how to simplify and all, because it will take time. So you have three equations, 1, 2, 3, right? You have three equations, three unknowns, right? You have three equations, three unknowns. So you can simplify and find the answer. The answer for F1 is going to be something around 95 hertz, right? It's going to be 95 hertz, right? So the answer is that, right? Fine. So let us move on to the next problem, right? So next we have to discuss the second question, right? So in the second one, they're asking the density of the material of the wire, right? They're asking the density of the material of the wire, right? So the density of the material of the wire, right? So fine. The density of this material, we know the diameter, right? We know the diameter. It is given to be as 50 centimeters, right? The diameter was given to be as 50 centimeters. 50 centimeters, and the length was said to be as, no, diameter was 1 millimeter. Sorry, the diameter was given as 1 millimeter, right? 1 millimeter. The length is given to be as 50 centimeters, right? So now, first of all, we need to find F2. So how to find F2? It's pretty simple, because now we know what F1 is. F1 is what? 95 hertz, right? 95 hertz, because we found it previously, right? So F2 is going to be 100 hertz, right? F2 is 100 hertz. So let's write the fundamental frequency equation for this string, right? We need to find what? The we need to find the density of the material. We need to find the density of the material, right? So density of the material. We have this equation. Can you guys remember? In theory, we did. That is, frequency is equal to 1 over 2L root T over molar mass per unit length. So mass per unit length is the total mass of the string divided by L, right? So further, you can write mass of this total string is rho into volume, right? Rho, volume is what? Area into length. So length to length cancel. So mass per unit length, we can find it as rho into cross-sectional area, right? So simply, for frequency, we can further write it as 1 over root 2L root T over M is rho into A, right? So we can substitute the values here. What was the frequency? 100 hertz, right? The frequency was 100 hertz, 1 over. What was the length? 50 centimeters. Write it in meters, right? What was the tension of the first wire? Tension of the first wire was 100 hertz, right? Yeah, 100 hertz. It was also 100 hertz, right? So substitute it here. Density unknown. Area is what? Actually, cross-sectional area. Phi the diameter was given to be as what? The diameter was given to be as 1 millimeter, isn't it? The diameter was given to be as 1 millimeter, right? 1 millimeter means what? Radius is 0.5, right? 0.5, right? Simply 0.5, it is going to be, right? Okay, radius 5r squared, 0.5 millimeters converted into meters, 5r squared, right? So you have to simplify this. And so simplification, of course, you will have to know that you have to scale both sides, right? So the left and the right, and then you can come up with the answer. The answer will be rho is equal to 12.73 into 10 to the power 3 kilograms per cubic meters, kilograms per cubic meters. So that would be the answer, right? Okay, that's given. All right. Okay, let's go for the next question. Right, so let's go for the 19th question. In this, of course, they're saying the first overtone, sorry, not the 19th, the 18th, we skipped 18th. Right, so the 18th question, in the 18th question, they're saying an underwater swimmer, right, okay, sends a sound signal to the surface, right? So, okay, from the below, somehow by means of a vibrator or something, he's sending some signals, right? So, if it produces 5 beats with the fundamental tone of a pipe of 20 centimeter length closed at one end, what is the wavelength of sound in water, right? So simply they're saying there is an underwater swimmer, so he is sending some sort of signals, which means by means of vibrations, so it's going to get vibrated. That's going to be a frequency. So, and also on the top of the water, so there is a one end closed tube, right? One end closed tube, so that is also vibrating. So when both these start to vibrate together simultaneously, it produces 5 beats per second, right? So they're asking the wavelength of sound in water. They have given the velocity of sound in air and velocity of sound in water, right? So yeah, simply let's see how it's done. 18th question, right? So the 18th question, what simply needs to be done is there is a water surface, right? So there is a water surface. Let's assume the surface of water, and some maybe let's assume that it's a tuning fork or something, right? It produces sound, right? So it goes to the surface. It goes to the surface, the wave, right? And then also there is a one end closed tube of length. What exactly? The length is given to be as 20 centimeters, right? So if I remember, 20 centimeters. All right. So they have, okay. So this is also vibrating. So let's assume the frequency due to this guy is the frequency of the sound wave due to this guy is F1 and due to this guy is F2. Now, can't we find F1? We can simply find F1. How? F1 is equal to V over 4L, because they have told that it vibrates with its fundamental frequency. The open end tube vibrates with its fundamental frequency. So F1 is what exactly? They have given the speed to be as 360 divided by the speed of sound in air is 364. Length is given 20 centimeters means 0.2. So F1 can be considered as, if we simplify, only 450 hertz, right? 450 hertz, right? So we know that if this is 450 hertz, right? They have also told that that produces 5 beats with the 5 beats with what? It produces 5 beats with this wave, right? This produces 5 beats with this wave. So it should be either F1 plus 5, sorry, it should be in this way, right? So it should be F1 plus. So the thing is, we do not know what is greater, right? So whether F1 is greater than F2, or we do not know whether F2 is greater than F1. We do not know. So therefore, if F1 is greater than F2, F1 minus F2 is 4 50 hertz, right? So in that case, the velocity of the wave or the frequency inside the water is going to be what? Sorry, this is not 450, it's 5, right? So it's 5, sorry, it's 5. It's 5, so 5 plus 450, f1 can be 455 hertz, or, right? Or if f2 is greater than f1, what is f2? F2, if this is greater, we should write it as f2 minus f1 is 5 hertz. We do not know, so we know that f2 sorry, here in this point there was a small mistake, right? That is, we have written it in the other side. So it should be, if when f1 is greater, who is f1? F1 is the sound which is produced inside a one enclosed tube, right? So if it is greater, what happens is, here we should decrease, we need to erase this, right? So let's completely erase this, right? So yeah, let's sorry about that, guys, right? So f1 is greater than f2. F1 minus f2 is equal to 5, right? What is f1? F1 is 450, right? Minus f2 is equal to 5. In that case, f2 is going to be 445 hertz, right? When f2 is whom exactly? F2 is this guy. If this is greater than the unenclosed tube's frequency, unenclosed tube's frequency, we found it to be as 450, right? So this can be 455 hertz. Both these are possible, right? This is also possible, this answer is also possible, right? So let's assume if this answer is the answer exactly, if this is the frequency of the let's assume the tuning fork which is inside the water, right? What we need to find is the wavelength. So simply v equals f lambda, and v equals f lambda. What do? We know that wavelength speed is given to be as 1450, and this is 445 into lambda. So lambda 1, we are going to get a certain answer, right? So we'll be getting for lambda 1 certain answer. If the frequency is f2, if it is 440 or 455, then once again we equal f lambda, we can find lambda 2, right? So that is 1450, the speed of sound in water, 445 into lambda 2. So lambda 2, you can get an answer, right? So there are two possible answers. We do not know exactly which that is. So therefore, like, the answers may be this or this, right? So if you simplify, it's up to you to simplify and check, right? So I guess that is understood here. Like, we can't exactly say what is the frequency, and then based on that, like, we can shortlist only up to 2 frequencies, right? So from there onwards, we have to find answers for both the frequencies, right? Let us go for the next question, that is the 19th one, right? So here what they're saying is the first overtone of an open organ pipe beats, which means produces a beat with the first overtone. Okay, the first overtone of an organ pipe produces beats with the first overtone of organ pipe, uh, which is 3 hertz. The beat frequency is 3 hertz. The beat frequency decreases with increment of length of the open pipe. It decreases with increase of the length of the open pipe, right? So the fundamental frequency of the closed pipe is 109 hertz. The fundamental frequency of the closed open pipe is 109 hertz. Find the lengths of the pipes. You need to understand the problem well. You need to pause this and then go through the question well, and then you need to start answering, like, go through the answer, right? So here 2 tubes are resonating, which are not resonating, like producing beat frequencies, right? So let's assume this is of length L1, and this is of length, let's assume L2, right? They have told that the closed tube has a fundamental frequency of what? Closed tube has a fundamental frequency of 109 hertz, right? So it has a fundamental frequency of 109 hertz, right? So if it has a fundamental frequency of 109 hertz, right, we can like we also know that f naught is equal to v over 4l, right? 4l1. So 109 is equal to v is 330, right? 4 into l1. We can simply find l1 in this case, right? So l1 can be easily found actually, right? So 109 into 4. Let me find the value of that using a calculator. So it was something around 0.75 meters, guys, right? So I just simplified. Right, so let's go for the problem now. So finding L1 is not going to be a big deal, but finding L2 will require some simplifications, and right, so we'll see what it is. Now they are saying in the question, right? Simply the first overtone of the open organ tube vibrates, or else vibrates with the first overtone of the closed open tube, then only they produce a beat frequency of 3 hertz, right? So the first overtone of this guy and the first overtone of this guy, right? If I'll call it as f f dash, right? So yeah, first overtone of closed one end closed tube is found. How exactly is that found? We can find, because like, they have given the overtone. F1 is equal to 3f naught, first overtone. I'm not going to say how I got these things, right? Because like it's pretty simple. We know that the first overtone is 3 times the fundamental frequency. They have given the fundamental frequency of the one end closed tube. It is 109 hertz. So therefore, you can easily find this, right? So F1 is equal to 9 times 3 is 27, 2 remaining, 3 times 0 is 0, and 2 327 hertz, I guess, right? So now we know that this frequency is 327 hertz, right? We can easily find this, because you know why? Because this is because f1 minus f1 dash is going to be 3 hertz. The beat frequency is going to be 3 hertz, and beat frequency is going to be 3 hertz, right? But in order to identify that pretty well, they have given the beat frequency decreases with the increment of the length of open tube. When we increment the length of the open tube, right, we know that, we obviously know this thing, right? So that is frequency is inversely proportional to the length. So when we increment the length of the, so what does this mean? Because now they're saying that the length, when the length of the open tube increases, actually what should happen for the frequency of the open tube? It should decrease. When the frequency of the open tube decreases, actually the beat frequency decreases. So the beat frequency, the open tube frequency is here or here. Think about it. Simply they are saying when the length of the open tube is increased, the beat frequency, sorry, the like actually when the length of the open tube increases, beat frequency decreases. This is what they're saying. So we actually know that when the length of the open tube increases, the frequency of that open tube decreases. So when the frequency of the open tube decreases, right, the this should decrease. So actually this should be the open tube should be in this point, at this point, right? So we have to rewrite this equation in this way: f1 dash minus f1 is equal to 3. Now it makes sense, right? Because when the length increments, then the frequency of the open tube decreases. When the frequency of the open tube decreases, this should also decrease, right? It makes sense, right? So therefore, that's fine. Now this is the equation we know. We already know that f1 dash is 327 hertz. So f1 dash is going to be what? 330 hertz. 330 hertz. So what is the open like first overtone of the open end is written how exactly? First overtone of that is the first overtone of an open end organ tube is written 2 times f naught, right? 2 times f naught dash. So f1 dash can be written as 2 times f naught is written how in open tubes. How do we write the open end f naught? V over 2 L. So let's say I told you this is L2, right? 2L2. So this cancels. F dash is 330 hertz. Sorry. V over L2. L2 is V is 330, right? Over 330. This is 1 meters, something around 1 meters, right? So it's not 0.5, I guess. There might be some issue, right? It's like correct it as 1 meter should be the answer, right? So this is 0.75, this is 0.75, and this is 1 meter, right? So like check for the simplifications also. I'm not quite sure about that since I simplified it a bit quickly. Yeah, as we've simplified, of course, it's 1 meter. So let's go with that answer, right? So the concept is the same, right? So like you can go with the concepts. All right. So let's go for the next question. So next we will be discussing the 21st question, right? 21st question. Let's go for that, right? It says a closed pipe and an open pipe sounding together produces 5 beats, right? So a closed pipe and an open pipe sounding together produces 5 beats if the length of the open tube is 30 centimeters. Now, length of the open tube is 30 centimeters. So what they are asking, the question, you need to read well the question. Find by how much the length of the closed pipe must be changed to bring the two pipes in unison. Unison means to bring the two pipes to vibrate in the same frequency, right? So this word unison might be new to you. So just remember that it means by how much we should change the length of the closed pipe to make them vibrate with the same frequency. So if I show you the question, right? So in a diagram, so this is the 21st question, right? So there is a closed tube and an open tube, right? So initially, they're saying the open tube is 30 centimeters. They have given the length of the open tube. Let's assume this is 30 centimeters. Do we know the initial length of the closed tube? No, let's assume it is L1, right? Now this is, let's assume in frequency F1, let's assume this is the frequency F2. These are not overtones, right? So this is just, I marked it as F1, F2, the fundamental frequency of the first wave. Okay, you guys might confuse it with the overtones, so therefore I will not mark it as F1, F2. I will mark them as F naught and F naught dash as usual, right? So fine. Now the thing is, so are they in the same frequency? Now think, are they in the same frequency? No. When they are vibrated, they produce a beat frequency of what? 5 hertz. They produce a beat frequency of 5 hertz. If that is the case, both should be in different different frequencies, right? Now, right, what they like, let's come for what they are asking later. For what, like, we actually need to find the initial length of this closed tube before we find by how much the length is decreased. In order to make these two frequencies the same, we need to first of all find the initial length of the tube, right? So let's do that. To do that, we are going to use this beat frequency data, right? So to do that, we are going to use the beat frequency data. So here, usually when they are vibrating in the same fundamental frequency, when they are vibrating fundamental frequency, who do you think is going to have the higher frequency? Obviously the open tube, right? We can't exactly say that the open tube has the higher frequency, it seems, because like the length are not the same, right? So like just saying, right, assume if the length was the same, right? If the length was the same, uh, the fundamental frequency of this f node dash, and if the length was the same, the fundamental frequency, obviously the fundamental frequency of the open end tube is higher than the closed tube. That is because like this is going to be V over 2f, right? Sorry, v over 2l, while the other thing, the closed tube is going to be v over 4l, right? So this is greater. So just assuming that, right? Just using that knowledge, I'm going to write this equation. Like actually, I'm going to assume this guy is higher, right? So if we do not assume this guy has to be as higher, we're going to get two equations, right? It's like sometimes this might be higher also. So to avoid two answers, I'm going to go with this, right? So it's up to my decision, right? Yeah, fine. I'm going to write f naught dash minus f naught. What will be the bit frequency? 5 hertz, right? So the fundamental frequency of the open end tube minus the fundamental frequency of the closed end tube gives us 5 hertz, right? Okay, so how do we write the fundamental frequency of the open tube? V over 2L2, right? Minus, this is fundamental frequency of the closed tube, V over 4L1. L1 do we know? We do not know, right? So if we substitute, V is what? 330. 2, L is what? L2 is 30 centimeters, right? 30 into 10 to the power minus 2 minus V over 4 L1. We do not know that, right? Okay, so we know the V, right? So let's substitute the value of V straight away. That is 330 once again. And if we simplify this, right? If we simplify this, we are going to get L1 to be as something around, I have already simplified that and found the answer, right? So it's going to be something around, give me a sec. It is going to be something around 0.51, right? 0.15, 0.1513, 0.1513, right? So just give me a sec. 0.1513 meters. This is meters. If it is taken in centimeters, it is what? 15.13 centimeters, right? So yeah, this is it. Now we have found the initial length of the tube, initial length of the closed end tube. Now what they are asking is, if you see well, by how much the length of the closed pipe must be changed to bring the two pipes to vibrate in the same frequency. We need to somehow change the length of this so that both have the same frequency, right? So somehow we need to do a small change, right? So that f naught is equal to f naught dash. So fundamental frequency of the closed tube is V over 4. Let's assume the new length of the closed end tube after we change the length of the closed end tube. It is L3. Now let's assume it is L3. But did we change the open end tube's length? No, it's the same. V over 2. V over 2 to L2, right? L2. So V cancels, right? 4 this cancels 2. So simply we are going to get an equation which is 2L3 is equal to L2, right? So L3 is equal to L2 is 30 centimeters divided by 2. This is 15 centimeters, right? So initially the closed end tube was the closed end tube was, right? It was 15 15.13 centimeters. Now, if they need to vibrate in the same frequency, this length of this closed pipe should be what? 15 centimeters. So therefore, the length reduction should be, right, from L1, it should be reduced to L3, right, which means 15.13 minus 15 centimeters. So we need to reduce the length by 0.13 centimeters. This is not very precise, the answer, but this is how you this is how you solve this problem, right? Go with the concepts. Do not worry about the simplifications and all. What matters is the concept, right? Concept. Okay, I hope that is clear. Let's go for the next question. Right. So let us go for the 23rd question, right? So here, the first few parts are simply theory. The question starts from this point, right? So they are saying an open tube A, right? So there is an open tube A of 60 centimeters long, and it contains air at 27 degrees. It contains air in 27 degrees. Different open tube B contains air in 67 degrees. Different open tube B contains air in 27 degrees. When both tubes are sounded with fundamental tones, beats heard are 5 hertz. Find the length of the tube B, right? If the speed of sound in air at 27 is 336, we need to consider that the speed of sound in air at 27 degrees Celsius is 336 meters per second. This is pretty simple, right? Fine. Let's go for the question, right? So these are some difficult, it's not difficult, right? So like in past papers, of course, the questions are going to be pretty easier than this, but if you try these questions only, you'll be able to somewhat figure out the past papers pretty easily. So this is what exactly? Open tube, right? So open tube, they're saying there are two open tubes, open tube A and open tube B, right? Open tube A and open tube B, right? So the open tube A is in what temperature? It is in 27 degrees Celsius, right? 27 degrees Celsius. Open tube B is in what temperature exactly? It is in 67 degree Celsius, right? So they are vibrating in fundamental frequencies, right? In their respective fundamental frequencies, but the lengths are not the same, right? So you need to understand that this has a length of, let's assume L1, right? This has a length of, let's assume L2, right? This has a length of L2. Open end tube has 60 centimeter length of 60 centimeters, right? Now, the problem, like, okay, so let's assume the fundamental frequency of this guy is F naught. The fundamental frequency of this guy is F naught dash, right? So we do not know now who is greater actually. Actually, we do not know who is greater, right? So whether this frequency is greater or this frequency is greater, we do not know that. So like if we know that only, we can exactly, if this is greater, if f naught dash is greater, we can write f naught dash minus f naught is equal to what? The beat frequency is going to be as 5 hertz. But we do not know that. So I will have to go with f naught minus f naught dash. F naught dash modulus is equal to 5 hertz. So I will show you only for this, right? Mostly you will have to find the other way also. Like I'm going to assume if f naught greater than f naught dash, right, then f naught minus f naught dash is equal to 5. You have to prove for what if f naught dash greater than f naught. Like in that case, you have to rewrite the equation f naught minus is equal to 5, right? We do not know that. So you have to once again find the length for this also. I'm not going to find for both. I'm going to find only for one, right? So I'll do it for this condition when if f naught if f naught, this fundamental frequency is greater than this fundamental frequency. All right. Okay, let's do that. So the speed of sound, like okay, f naught v over 2 L1 minus v over 2 L2 is equal to 5, right? The fundamental frequency of a open end tube is v over 2L1. V over 2L. Fundamental frequency of an open end tube is v over 2L. So here what changes is this is L1, this is L2. Is this correct? Is this correct? This is not correct. Why? Because this tube is in 27 degrees Celsius. This tube is in 67 degrees Celsius. So when the temperature changes, velocity of sound in air also changes. So this is the velocity of sound in air here is v1. The velocity of sound in air here is v2. Right? We know we have an equation for velocity of sound in air. V is equal to what? Gamma r t over capital M. Therefore what? Therefore we can say that velocity is directly proportional to root of the temperature. Right? So right, that is it. We need to now find the velocity. Like they have given when the temperature is when the temperature is 27 degrees Celsius. They have given the velocity was to be as what? Velocity to be as 336. Right? When the temperature is 27, they have given the velocity to be as 336. Right? If so, we have to find when the temperature is 67 degrees Celsius, what is the velocity? We need to find this. We know that v1 over v2 is equal to what? Root t1 over t2 by using this equation, right? So when the velocity is v1, temperature is absolute temperature. 27 means 300. When the velocity is v2, absolute temperature is 67, right? So it makes sense. v1 is given to be as 336. v2 is what? v2 is going to be what we need to find, right? So T1 is what? Temperature, absolute temperature 300, and when it is 67, absolute temperature is going to be 345. I'm correct. So velocity v2 can be written as what? v2 can be written as 336 root 340 minus 300, right? So this equation I'm going to rewrite. So this is what? v1 and v2. v1 is what? v1 is 336 minus 2L1 2 into what is L1? L1 they have given to be as 60 into 10 to the power minus 2. What is v2? v2 is, we have found v2, velocity of sound in air when the temperature is 67. That is 336 340 divided by 300, 1 over 2 L2. This is what we are going to find, right? So what is the beat frequency? 5, right? If we simplify this, we are going to get L2 to be as I guess 63, and when this is what when this is the case, we're going to get L2 to be as 65 centimeters, I guess, right? So this could interchange. I did not simplify and see, but simply this is the method, right? So if you couldn't understand the method, once again you have to go through. Like the only change here is the temperatures are not the same. If the temperature is not the same, the velocity of sound in air will also change, right? So here the velocity changes as well as the velocity length. So when you apply the beat frequency equation, you have to be very careful, right? You have to use this equation as well, right? So yeah, I hope that was clear.